So what we want to do is kind of compare and contrast the stuff we've been doing, those linear functions, the power functions, with a new function, exponentials. So we'll recall for a minute here that y equals x squared, or y equals, say, x to the third, is what we call a power function. So when you have the variable is the base of the exponent, and the exponent is just a number, that's known as a power function. But something like y equals 3 to the x, so if you switch what you have as the base and what you have as the exponent, then this is no longer a power function. This is what we call an exponential. And so they behave very differently. It's sometimes easy to get them confused, but they act very differently. They have different characteristics, and we want to try to talk about that a little bit. Now, we're also going to compare and contrast linear functions with exponentials, and you have probably seen a little bit of this before. So we know that linear functions have a constant rate of change. So I'm going to say have constant rates of change. Linear functions have constant rates of change. So, for example, if you have, say, $100 and you spend $8 a day, then how could we write an equation to say how much money you have after X days? So how much money Y you have after X days. Is that too cold over there? Oh, if you're putting on shoes, things have gotten drastically cold.
Negative 8x plus 100.
Very nice. Okay, so because this is your rate of change and it's constant, it's going to be linear. And the rate of change is our slope, and it's decreasing, so it's going to go down by 8. And the amount we have at time 0, our y-intercept, is going to be the 100. So compare or contrast that with, so we'll say that an exponential function, so whereas a linear function has a constant rate of change, an exponential function increases or decreases by a constant percent. Increases or decreases by a constant percent. So, as an example, if we said you have that same $100 to start with, you have $100 again, but you invest it. You invest it and say earn 5% per year. So it's increasing by a constant 5% every year. So let's take a look about why that ends up to be an exponential and how we're going to get the different parts of that. So an exponential is always going to be something in the form y equals ab to the x. That's what we mean by an exponential. And so if we start with $100, so then after year 1, so when x is going to be 1, then we will get the $100 that we started with, plus we're going to get 5% of that $100. So we're going to get that 100 times 0.05. That make sense? And so we're going to do a little algebra on that and factor out the 100. Tell me if I start going too fast here. And we're left with 1 plus 0.05, and so that's going to be 100 times 1.05, and we know that's going to be $105. And that's not as important as what we're going to get for an equation out of this. So after 1 year, we got 5% more than what we started with. So then, in year 2, you're going to take that $105, because now the interest gets a chance to earn interest, is compound interest. And then you're going to get that $105 times a 5% in the second year. Does that make sense? So we can do our same game of factoring out that 105, and we'll be left with you with me? Did I lose you? Any nods of head? You okay with what I've got right here? Okay, and so we factor out the 105. What's left is 1 plus 0.05 again. Okay, so far. But now that 105, right, we got that 105 from 100 times 1.05. So I'm going to replace that 105 by what we called it there. There's 100 times the 1.05 times another 1.05 makes that 1.05 squared. So here's where the exponential piece comes in. That makes sense? So what would it look like then after the third year? So when x is 3, and we just jump to it, then we're going to get 100 times 1.05 to the third. So as an equation then, we would get y is going to be that amount we started with times 1.05 to the x power. So we get this a times b to the x. Does that make sense? And the a, this a, is what we get when you plug in 0 for x. Right? B to the 0 is 1, and so at times 0, the starting amount, what we often call the initial amount, is going to be that a, which is really the same thing we get, I mean, the parallel with a linear function, right, is right there, because the initial amount, we don't usually call it initial amount in a linear function, but when you plug in 0 for x, you get the b. And so the y-intercept is your initial amount in a linear function, and the a is the initial amount in an exponential function. Now, in a linear function, the m holds this information. It holds that average rate of change. That m is how much is it increasing or decreasing by each time period. And what we see in an exponential is that this b holds this information as well. The b is going to be 1 plus r, where r is that percent, and it's going to be either an increase or decrease. So if this is decreasing, then instead of adding that percent change to a decimal, right, 5% was how what this was increasing by, we made it into a 0.05 to actually do arithmetic with it. So the percent changes to a decimal. This r holds that percent in it. So anytime that b is bigger than 1, then how much bigger than 1 is going to be the percent that it's increasing by. And if this b is less than 1, then what we have is that b is 1 minus r. So it's also telling us that information by what percent is it decreasing by each time, whatever the time value is for Rx. Does that make sense? This is something we're going to build on and talk a lot about here. Okay, so let's kind of summarize a little bit here. Well, I think we've said that. So let's say, let's do an example here. So a car decreases in value by 20% each year. You smell that smoke, can't you? So a new car, we'll say a new car is $25,000. Maybe it's a new used car. I don't have to buy a new car. 25,000 anymore. So can we find an equation where y is going to be the value of the car, and should we use, you want to use t or x for the time? X, okay, we'll use x's and y's where possible. I'm okay with that. Okay, so y is going to be the value of the car after x years. Okay, so see if you can come up with an equation. So, anybody, what's it going to be?
25,000 times 1.2 to the x.
That sound right?
If it's decreasing in value, wouldn't it be 0.8?
Exactly. So if it was increasing by 20% each year, then that would be a 1.2. But our b in this case, because it's decreasing, is going to be a 1 minus r. So we're going to take that 1 minus 0.2, which is our 20%, or we can just call that 0.8. Does that make sense? Okay, so what we're seeing then is that when we have y equals a b to the x, okay, the a is going to be what we have called our initial value. The b is going to be either a 1 plus r or a 1 minus r, depending on if this is increasing or decreasing. And when it's increasing, we call this an exponential. So in this case, we call it an exponential growth function. And if that is 1 minus r, we're going to call it an exponential decay function. Okay, so we have exponential growth or exponential decay. So when the b is greater than 1, that means we're going to have growth. And when the b is less than 1, talking about y equals ab to the x here, then that's going to be a decay function. Either way, we're going to call b that b, which is going to be either 1 plus or minus r, we're going to call that the growth factor. So even if that's less than 1 and we're actually decaying, that's going to be our growth factor. That's what we're multiplying that initial amount by each time we increment x up. That's going to be called the growth factor. All right, so I'm going to give you some equations and ask you some questions about it, just to make sure that we can understand here how the different pieces work together here. So let's say first, is it going to be a growth or a decay? And be prepared to say how you know that. Is the equation that I'm going to give you here, does that represent an exponential growth function or an exponential decay function? Then I ask you, what is the growth factor? So can you identify what is that growth factor? And can you tell us what is the percent increase or decrease? So we're looking for that R. So by what percent is this, whatever it is we're talking about, increasing, or by what percent is it decreasing? And can you identify what is the initial amount? Okay, we understand the questions? So I'm going to give you an equation. You can think about it, talk about it with somebody in your zip code, and see what we come up with. So first we'll say y is 30,000 times 1.06 to the, and I'm going to use T over Ashland's objections, but you can write it as an X if that makes you feel more comfortable. And see what we get there. Definitely, yeah. So y equals 30,000 times 1.06 to the T. Is it a growth or decay function? Yeah, what is the growth factor? What percent is it increasing or decreasing by? And what is the initial amount? Speaking is encouraged.
Yeah, I guess it's no.
You listening in, Parker, or you're on the island there? Okay, so growth or decay, how did you know? Because the base is bigger than 1. 1.06 is bigger than 1. What is the growth factor? 1.06. So it is exactly that b in y equals ab to the x. So 1.06 is going to be growth. And what is the percent increase or decrease? 6% increase, because it's bigger than 1. However, you just subtract 1 from it and then make it into a percent. And what was the initial amount? 30,000. Okay, let me give you a different one. So let's do y is equal to, and we'll say 35 times 0.87 to the t power. Same questions. Is it growth or decay? What's the growth factor? What's the percent increase or decrease? What's the initial amount? Don't touch that calculator. Yes. Comforting knowing it's there, just in case.
Like, okay, because this would take a while, but like when that, like, you know, like, all of them.
So Jeremy, growth or decay? Decay. And what is the growth factor?
0.87.
Good. And percent increase or decrease?
13% decrease.
Good. So make sense how we got that? So you either subtract, you can either say that's 1 plus r is 0.87 and subtract the 1, and when you get a negative 0.13, the negative is indicating that it's decreasing. Alternatively, you could say because that's less than 1, you can call it 1 minus r, and then if that makes you feel better that you're going to get a positive number for r, either way. So you can either say it's decreasing by a 13%, or you could say that the change is a negative 13%. Just be careful you don't say it's decreasing by negative 13%. Why would that not be correct? Yeah, it's a double negative, right? So decreasing by a negative 13 is really mean increasing by 13. So just be careful how you say that. Okay, and what was the initial amount? 35. Okay, so let me give you another one. Same questions. Let's say we've got y equals 10 times 2 to the t. So growth or decay, what's the growth factor? What's the percent increase or decrease? What's the initial amount?
I got growth. The growth factor is 2. It's increasing by 100%, and the starting value is 10.
I said it should be not one.
I said increasing by 100% because it starts at 100 and then you add 100 to get.
Grace, were you listening in on all that? No? Just ignoring them. So Grace, growth or decay? Good. And what's the growth factor?
2.
Good. And what's the percent increase or decrease? Yeah, good. And sometimes that bothers people once you get, you're not seeing that decimal in there. It's still going to be that. Subtract 1 from it, make it into a percent. What was the initial amount? Nice. Okay. So let's graph this for a minute. I just want to point out something because we've talked about concavity in the past. So let's just talk about what the concavity is for an exponential growth or decay function. So let's look at the graph of y equals 2 to the x. So I'm just going to plot a couple of points here, and then we'll talk about this idea of concavity. So when we plug in 0 for x, we know that 2 to the 0 is 1. So we're going to contain the point 0, 1. When we plug in 1 for x, we're going to get 2 to the first, which is 2. So we have the point 1, 2. When we plug in negative 1 for x, we get 2 to the negative 1, and 2 to the negative 1 is 1/2. So I think we can get enough here to get an idea that there is 2 to the x, and this is the basic shape of any exponential growth function. So with the a here being 1, that a is going to be our y-intercept. So this is really like 1 times 2 to the x. So if we're thinking of this as ab to the x, the a is 1, and we're going to see that because that's going to be the y-intercept. When we plug in 0, we're going to get 1. And because our base is bigger than 1, it's going to rise from left to right. We're going to always have this horizontal asymptote of y equals 0, unless we add or subtract something to that to translate it up or down. Okay? Now to look at concavity, so if I think you can see that this is concave up or concave down, which? Concave up, because it's bowl shaped up. So our function, I'm going to say, we'll just say it's going to be concave up. We can see that, remember, what it means, our definition anyway, for concave up is that the rates of change are going to be increasing. And so the rate of change between these first 2 points here, remember that's our change in y over change in x, or just our basic slope formula. So if I take the 1 minus the 1/2, those are the difference in the y coordinates. You with me here? And then the change in x is going to be 0 minus negative 1. And so, what did I not do right there? 1 minus 1/2, 0 minus negative 1. I should be getting a positive slope, but I'm not.
That is positive.
That is a positive.
That is positive. It was my subtraction of 1 minus 1/2 that was getting in my way. So there's the rate of change. There is a positive 1/2. And if we look at the rate of change on these next 2 points, then we're going to again go to change in y, 2 minus 1, and then 1 minus 0. And so that turns out to be 1. So as we work our way from left to right, we can see the rate of change is increasing, which means it's going to be concave up. Okay? Just making that point where we can, reinforcing our idea of concavity. So So we're gonna do something a little more challenging now. You're gonna need a graphing calculator. So if you got one, break it out. If not, I've got some rentals available in the suitcase over there. So I'll write it down here. If an investment increases by 4% per year for 10 years, by what total percent? By what total percent did it increase? If an investment increases by 4% per year for 10 years, by what total percent did it increase? So at first guess, I mean, first glance, you might say, well, this is really obvious. It increased by 4% every year for 10 years. 4 times 10 is 40%. It increased by 40%. But that's not correct, because what's happening here is the compounding. So after that first year, your investment's going to increase by 4%. That increase is going to be added to the principal, what's earning interest. So the next year, you're going to have more than what you started with earning interest, and so on. So it's the power of compounding. And this is, again, the difference between an exponential growth versus a linear growth. Because if we were talking linear and something was increasing by 4 each time, after 10 years, it would be 4 times 10 is 40. So what is our equation going to look like? Since this is increasing by a constant percent, it has to be exponential. So we're going to get something that looks like y equals ab to the x. And what's the a and what's the b?
10 times 1.04.
So what is the a? Do we know? We don't. So we can just leave it as a. What's the b going to be? Good. So it's the 1 plus r. And remember, you got to change that percent into a decimal before we can do any arithmetic with it. So that becomes 1.04. And then the exponent, the x, is going to be 10. So on your calculator, you're going to multiply that. You're going to take a 1.04 raised to the 10th power. And when you get that, you can give me, oh, I don't know, let's go maybe 5 decimal places, something like that. Understand what we're doing?
So 1.48
Okay, anybody not getting that? Okay, so after 10 years, we're taking, remember A was our initial amount, we didn't know what that was, but after 10 years, we're going to multiply, we have a factor that we're multiplying it by of 1.48024. So this now, again, holds that 1 plus r. Only the r now is not the percent it's growing each year. This is the percent it grew over that 10 years. So just to the nearest percent, because this rounds pretty nicely, what did it increase by? Can you tell? It increased by
148.
not 148, because remember this is 1 plus r. So if we subtract off that 1, right, it's what we really want is how much bigger than 1 is that? That's the r part right there. So the r is going to be that 0.48024, or we can say it's going to be about, once we change that decimal to a percent, it's going to be 48%. So maybe surprisingly, if you haven't worked much with exponentials before, increasing by 4% every year, but letting it compound for 10 years does not increase your investment by 40%, it increases it by 48%. So remember, we're tapping into, this is an exponential growth. So, and this is why, people try to talk about, when you're your age, if you're saving money, saving a little bit now, the big part of that exponential growth comes later on. So we gain an extra 8% here in 10 years. That's going to get even bigger over time. And so it's having an investment that you can allow grow over a long time, 20, 30, 40 years, is where you get the huge growth out of that exponential part of that, as opposed to linear. Okay, let's turn around the other way and make it a decrease. So, and see what we get. So you buy a car, and say buy a car for $30,000. It is going to, you will say it depreciates. That means it goes down in value by, we'll say, 50% per year. Let's not say we know what it's, because I don't want the 30,000 to get in the way. I want to do like before. So you buy a car for, we'll say, P dollars. Okay. By what percent does it decrease by in 5 years? So we taking 0.85 to the fifth? And can somebody tell me we got to like 5 decimal places?
0.44371.
44371. So how do we get from there to the percent it decreased by in those 5 years?
Subtract 1.
Subtract 1 from that. And so that's going to turn out to be negative. And what are we getting? Like 5, 5, 6, 2, 9. Does that sound right? How's that for mental arithmetic there? Huh? And so changing that to a percent, that's going to be a negative 55.629%. You with me on how we got that? I need nods of heads. Okay, so we're going to say it decreased by almost 56% over those 5 years. So it's worth less than half of what it was. Oh, such is life, huh? Okay, questions on this? Okay, so we'll be doing more with this in the days that come. Let's go and do some practice problems like we started with at the very beginning of class, but I'll add some new twist to it. So some practice with exponentials, and you simplify, say 2 to the negative 1 minus 2 to the negative 2, all to the negative 2 power. Now this is very tempting to do something that is not correct mathematically. There is no distributive property of exponents over addition or subtraction. And it's so hard to resist just applying these negative exponents there, but that is not correct. You cannot get to the right answer that way. What must we do?
Convert it to a fraction.
Yep, make these into fractions. Once they're into fractions, then what?
multiply by the square root, or square root both.
There's no equal sign, so you can't do the same thing to both sides of the equal sign. You're gonna have to deal with that -2 eventually, but not yet. Once you got the fractions, what are we gonna do?
Common denominator.
Common denominator and do the subtraction of fractions. Once you have made that into a single fraction, now you can apply the -2. So you can either take each numerator and denominator to
Please
-2, or
excuse the
it'd be
interruption.
nice to
All seniors
reflect it and
meet
then
in the
square it.
main gym at the beginning of second period. Both sides of the gym will be available, so please make sure you're spreading out and practicing social distancing. Thank you.
You okay to hear? Common denominator, so the 1/2 is gonna become
2/4.
2/4. We okay? And 2/4 minus 1/4 is 1/4. And I don't know how you do this. I like to apply the negative part of the exponent and flip it. And then take it to that positive exponent. So we're trying to get 16. Crazy. Oh, you think these exponents are easy? Okay, oh, 1 minute. Do I have a 1 minute problem? I don't know if I have a 1 minute problem. Let's see. See if we can do 3n to the -2/5 times n to the 12/5 minus 3n to the 7/5. All right, the clock's running. I'm feeling the pressure. What do we need to do? Can't hesitate. The clock's running. What are we going to do? Frozen. We're going to distribute, of course. We're going to multiply the coefficients. 3 times 1 is? Whew, that was really going to be tough. What are we going to do with the exponents? No. When you multiply the powers, you add the exponents. -2/5 plus 12/5 is 10/5. 10/5 reduces to 2. Ah! 3 times -3 is -9. Add the exponents, we get 5/5, which is 1. There is your answer. Whew. Paralyzed.